Hi, everyone. Today we are going to be presenting on the Supreme Court judgment predictions. I'm Hailey Naugle.
And I am Brandon Owens.
Okay, for our presentation, we are going to run through our data, the preparation, the EVA, and the models that we created. So let's start with the data. So these are our data sets that we found. We have one on the Supreme Court cases, one on the judges, and one on the US presidents. I'm going to kind of go through each one and talk about how they are connected. So first we have Supreme Court cases, and this is kind of what our data looked like. From this data set, we are going to use the term column to connect it to our next one, which is the Supreme Court judges. This is what this data looked like. And here we took the term from the last data set and we matched it. So it was a match as long as it was in between the start and the end of the justice term. And then to connect this to our last data set, we are going to be using the appointing president. And the way we did this was we had another data set, which was US presidents. And we matched the name of the president from the previous data set to the party in this data set.
And then in order to match these up, we make a party affiliation assumption where we assume that the Supreme Court justice who is appointed, so in this case, our example would be John Rutledge, who is appointed by George Washington. We take George Washington's party that he identified with, which George Washington was an independent, and then we merge these two. So we assume that John Rutledge is associated as an independent Supreme Court justice. That's where his party affiliation lies. And then we're going to go into the preparation. So what we did with our data outside of just loading it in. First thing we did to clean it up, we got the judge's start year and the end year in date-time format because it was previously just in string format. Then we matched the judge to the party affiliation, which is what we just kind of mentioned, where we matched up what year they were brought in and what the president of that year's party affiliation was. And then we have to make another assumption. So here, if let's say the parties have changed over the years, and there used to be a party that existed called the Democratic Republican Party, and that does not just mean that you're a Democrat and a Republican. They actually identified more with the Republican side of things. So instead of just going strictly party, we make another assumption that some of the parties will either lean more left or lean more right, or if in the case that they're an independent, like the George Washington example, that they will actually be neutral. So we go through and we map out each case, how many justices were conservative, liberal, or neutral. And then we remove missing rows from data that we're going to use later in the issue area and the first party winner, which is actually going to be our target variable.
So this is an example of what the merged data ended up looking like. You can see all the way on the end, we have 3 new columns that we didn't have previously, one for conservative, one for liberal, and one for neutral.
And we wanted to focus and try to challenge ourselves a little bit with natural language processing. And we just went into some simple approaches here. But on the left side of the screen, the big function you see there, the tokenizer function, basically just takes each row, so each case from our cases data frame, and there's a fact statement that's associated with each row that is basically listed as the Supreme Court writes off a fact statement for what the case entails. We break it up into individual tokens, and then we kind of regularize. So we get rid of like any capital letters, and we get rid of all of the punctuation and stop words. So words that are kind of useless for any sort of analysis, like the, I, a. And we do this for every single row so that we just get the important phrases or words in a format that we can identify how important they are for the words that are chosen, to try to get an idea to see if the judges are biased in any way when they write the fact statement. And the way that we kind of do this is after we regularize it, we do something called a count a vector or a vectorizer, in which it's a bag of words format where you create this matrix where every single token is on as a column, and all the documents are rows. So in the example that we have here, you can see in the bottom right, this, let's say the fact statement said about the bird, bird, bird. You can see that bird is said 5 times. So the count matrix just has, for every single token that is said in there, a count of how many times it's said. We also do another feature, not accounts, but it's called TF-IDF, and we'll get into that a little bit later.
Okay, so these are the features that we ended up using when we made our models. So the first one is the term, or like the year, which we talked about a little earlier. The next one is the ideologies, which we also talked about. And then the last one is the issue area. So whether that was, I think, like capital punishment, like whatever the different issue areas for Supreme Court cases are. And those were all binary. We created dummy variables for those. So that's how we use those. And then there were 2 NLP, which we kind of talked a little bit about, the TF-IDF. That's what the...
Yeah, more specifically, so instead of it being like the count vector, where it's just a count of the tokens, the TF-IDF tries to get a weight for if a word is said a lot across all of the documents, it's less important. So you get the term frequency. So like, let's say a term said 100 times, then you multiply it by the number over the document frequency. So that'll dumb it down. It'll have a way lower weight if it's said over all the documents, so it's less important. So it helps distinguish unique words that are from document to document. And then the bag of words, which is the count matrix that we talked about earlier.
And then the next section is our exploratory data analysis. So for this, we just made a whole bunch of graphs. We started just by mapping out the years that these cases were. We see that the majority of the cases were between 2000 and I believe the most recent cases we had on here was 2022. So that's just the distribution of cases by year. And then we also created a plot of the first party winner. So this is our explanatory variable here. We have whether the first party wins or doesn't win. In Supreme Court cases, the first party is called the appellant. So they are the one who appealed the original decision. And so we can see from this that about 67% of the time, the first party does end up winning. And so that's what that graph looks like. And then we kind of split that up based on the issue areas that we talked about. So we can see that it does remain true for all of the case or all the issue areas that the appellant does usually win. And we can see that for each of these areas, the blue line is higher than the purple one, which means they won most of the time. Then we also did this for the ratio of conservative to liberal judge ideologies. And we didn't really see any crazy differences there. Most of the time, the first party does win in each of those areas. And then the last thing we did was with the NLP, we took the counts of words and we created this graph. So what this tells us is basically the word sanction is said the most times throughout all of the facts, followed then by persuasion and so on.
And then the modeling. So what we do first is we created a baseline or a null model. And to do that, we kind of looked at what the different decision types were, because there were a lot of them. There were reverse remanded, affirmed, vacated, remanded, reversed in part, vacated, or vacated in part and remanded. And you can go through and read these if you'd like, but basically I'll sum it up. Our null model looks at, just assumes that the lower courts that issue their decisions to the Supreme Court, or the appellant appeals the issue to the Supreme Court. We're going to assume that every single time that the court is not going to reverse any part. So they're not going to reverse remand the decision. They're not going to reverse in part, or they're not going to vacate or nullify any part of the original court's decision. So anything that involves the word reverse, we're just going to say that that didn't happen. So we're just assuming all the other cases, so that the lower courts are always right, and our justice system hopefully always gets everything right, which we know is not always true. But so Then we went through and we ran first the no NLP section. This we just ran our features that didn't have any NLP. We ran it through logistic regression, decision tree, random forest, and k nearest neighbors. Here the logistic regression performed the best at about 66.7%. Then we did only NLP, where we ran the counts matrix and the TF-IDF matrix as our different features. And the random forest for the counts was the best at about 66.8, so not barely any better. And then we combined the features and the NLP, and we ran a little bit different because we saw that we wanted to try the XG gradient boost, and we wanted to try or we kind of shied away from random forest and k nearest neighbors. And we saw that here the best was the decision tree for the counts, which is surprising that it performed a little bit worse than only the NLP and the no NLP, but it was more precise. Like all the measures were around each other. And these models are all outperforming for the most part. I guess our best models are outperforming the baseline, which ended up having about a 64% accuracy. So it's about a 1 to 2% difference. In this case, the best model was about 2.8% better accuracy, which I mean 2.8% accuracy is it's minimal, but at least it's a little bit better. And when you're making decisions that are impacting the nation and people's livelihoods, I guess 2.8% isn't that bad. And that is all we have. If you have any questions, feel free to reach out to us. We also have, this is on my GitHub. Hailey and I collaborated on this. It's labeled as MIS 5470 _ Supreme Court _ decisions. Where we have the README, we have we have links to the different Kaggle data sets that we use, the images, the results, and we skipped over some of the code in here just to make it more visually appealing and walk through it. But if you want to see how we did every single step, because there are steps that can kind of just be assumed, you can go in there and check it all out for yourself and get a good feel for it. But,
Thank you.
Thank you.